All right, welcome back, everyone. Let's take a minute to talk about the final exam. This is the only thing we're doing this week is preparing for the final exam, which will be starting, of course, next week during finals week. It's going to be very similar to the previous exams, and I will open it up. You'll have a window just like before. I'll open it up at 5 a.m. Monday. That's December 14th. And it'll be open until 5 p.m. Friday, 12/18. So anytime during that whole finals week, you can go ahead and start the exam and finish the exam. The primary difference is that the semester exams were 50 minutes. This one is 2 hours. So if you want the full amount of time and you're a procrastinator, the last minute you should start it is 3 p.m. on Friday. But just find a 2-hour time in there to complete this exam. Open book, open notes. So similar to, like I said, to the other exams. No internet. You can't use others, friends, anyone else like that, right? Also, I should say that to have information available to you, I would have the information of the moments. Remember, we talked about 2 different moments. One was the maximum moment if I had a point load in the center of the beam, and the other one is if I have a distributed load throughout the entire beam. Those are the only 2 that you would need to know. What is that maximum moment for those 2 loading scenarios, right? Is it WL squared over 8 or something similar? So yeah, know those 2. Also, your I-beam tables. So we said based on that maximum moment, you need to figure out what size I-beam. That was based on this thing called a section modulus. We'll talk more about that in just a second. But then we looked for the lightest I-beam that could handle that moment. So and those were using the same tables you should have available. Deflection equations, remember those, where you can just plug it in, find out how much the beam has deflected down. And all those 3 tables should be found in week 16 under the final exam review tab, right? So take a look at that. So that's a basic overview of the exam. Let's get into the content for each individual section. So the first thing that we talked about was what I was calling intro to materials. These were done via PowerPoint. You can go through and look at those. I just tried to highlight everything in there. There's a lot more information in here, probably more detail than we need, but it's good to go over. We talked about the chemical composition of materials, and we defined compounds versus alloys versus mixtures. Compounds are 2 or more elements, like water, bound together. Alloys are the same thing. Alloys are a compound. The only difference is we have metal as one of the elements and then some other element. Then we also talked about mixtures. It can be elements or compounds, but the idea is that they can be separated, like oil and water, right? Mixed together, but then can be separated. That's the difference between a mixture and a compound. We talked about bonding. We said there were 3 different types of bond: ionic, covalent, and metallic. Ionic bonds mean that basically your 2 atoms, one is giving up an electron, the other one is receiving it, creating a positively charged ion and negatively charged ion, which that creates the bond. Talked about covalent bonding, where they're sharing some electrons, and a metallic bonding, where there's like an electron cloud going around all of your atoms. Talked about molecular structure, 2 types, amorphous and crystalline. Amorphous means there's no pattern, versus crystalline means there's a lattice structure to it. Metals fall under that crystalline type of lattice structures. In fact, I think we even had a slide showing various metal lattice structures. Then we also had a slide talking about material properties. The different material properties when we're defining materials could be general, chemical, physiochemical, mechanical, thermal, electrical, magnetic, acoustic, and optical. Of course, mechanical is what we focused on most in this class. That's really like your strength of your material, right? We weren't so concerned of thermal properties. And we moved on to standards. If we're talking about structural systems, they're governed by ACI, AISC, AISI, ASCE, ANSI, and ASTM. Electrical, NEMA, IEEE, and ASTM, and mechanical, ASME, and ASTM. You notice that ASTM are in all of these. So ASTM is like the governing body, at least for testing, to verify that our materials are where we need them to be, right? So because of that, we spent more time on ASTM. We said there's categorized in different sections and letters. And there was a slide on that. The most important one for us was section 4, the construction section. But there were, I don't know, 13, 15 different sections. There are also letters, which are groups within the section. So like, for example, if we had A, that means ferrous metals. I think B is non-ferrous metals. But regardless, the idea is that ASTM is categorized into sections and letters, right? That was a lot of information there, and you could get really technical on all that. Don't expect the final to get too detailed, right? This is more of an overview type of thing. So let's move on to, after we talked about that, we talked about this concept of stress. And the fundamental principle behind this idea of stress is that we can have forces on an object, right? We can pull it or push it or bend it or twist it or karate chop it, right? Those are the forces we talked about. Each force creates a stress. So we talked about these throughout the semester, but in summary, when we talk about a pulling, a tension, or a compression for a force, we end up with a stress. I can see over on this other side, right? I have sigma is equal to whatever force I'm pulling with divided by that cross-sectional area. So those problems had to deal with like how much force is applied, what's the area that's applied over, divide force by area gives the stress. We talked about the shearing stress. Same idea, but now we have a shearing force and the area is parallel to the cut. So I'm cutting this way. If I were to look at the cross-section, it's parallel. We talked about torque. So torque was the twisting, right? With the twisting, we introduced some new variables. We said we had, well, going back to shear, we introduced the variable tau, which meant shearing stress, shear force over area. Torque also gives us a shearing stress, so it's also a tau. It's equal to the torque applied times c, which was the radius, over j, the polar moment of inertia. I'm going to go into all these in just a second. This is just a basic overview. And then last, we talked about the bending moment. Makes either a smiley face or a frowny face. This is a positive moment. This is a negative moment. And we had an equation for the stress. We have that sigma again. So sigma meaning it's the same thing as a compression, a tension, or a compression. So we get that same sigma. In this case, the equation was my over I. M was how much that we're bending it, y distance from the center, I moment of inertia. Like I said, we'll talk about those individually. So starting with this idea of tension or compression, like I said, we have a stress, sigma, which is the force divided by the cross-sectional area. So the force is magnitude, force I'm pulling with it, usually in either kips or pounds. And then we have cross-sectional area measured in inches squared, right? How do I find the cross-sectional area? There was one thing where if it was a circle, we said, well, you can use pi r squared for the area of the circle, which most people know, but we said it might be easier to use pi over 4 d squared. But that was the idea behind tension and compression. So let's move on and take a look at shear. So with shear, it's like we're doing a karate chop, right? Where we have a force going this way, and the break in the plane would be along the same direction. Our equation was tau is equal to V over A. So our shearing stress is equal to our shearing force. Try that again. Shearing stress is equal to our shearing force over our sheared area. This is where we moved into connections. We said, well, you really have to be careful on the number of shear planes. So what I'm showing you here is a pinned connection. How many shear planes would this pin have if it were to break? Well, you can see it would break here and here. Basically, I have 2 shear planes would end up in 3 separate pieces, right? So these questions are basically looking at sheared area, the number of shear planes. That's what you really have to focus on, right? And shearing force is usually given in the problem in some type of way. After shear, the next type of stress that we looked at was torque. So remember, the torque is the twisting of our member, and we had another shear stress, T, C over J, those variables. T is the torque, how much I'm twisting, the twisting force. C is my radius. This is a little weird because it's not a round cross section, but you can imagine if it were round, it's the radius of this member. J was a new term called the polar moment of inertia. And what J is, we had an equation. I had it as C. I didn't want to confuse too many people, but basically it's either pi over 2 times the radius to the 4th power if it's solid, or if it's like a pipe, meaning this part is cut like that, I have pi over 2, the outside radius to the 4th minus the inside radius to the 4th. So that's how we find the polar moment of inertia. Plug it in, we can find our shearing stress on our object. And those values can be looked up in a table. What is our allowable shear stress? And so we can see if our drive shaft or whatever's twisting is going to break or not, right? The other type of stress we talked about was a bending stress. So with a bending stress, we could have a positive bending like this or negative. But we had a basic equation. We once again have this sigma value, meaning it is a axial, a tension or compression type of thing. Our equation was my over I, where m is the moment, right? So this is what we were looking up from these moment diagrams. But you can find those moment diagrams. It's basically just plugging in forces, whether it's distributed load or a point load, but you can find out what the maximum moment is. And then we have y is our distance vertically, either up or down from this, what we're calling neutral axis, the center of our cross section, right? And then I was our moment of inertia. Now, most usually this y value is the distance. It's like half your height, right? So if you have a 12-inch deep beam, then that y value is going to be 6. It's almost always half. The only way it wouldn't be half is if you wanted to know the bending stress somewhere in the middle of the cross section, which is usually you just care about the worst case scenarios, which is the top or the bottom of the beam. We define this moment of inertia. We had an equation 1/12 bh cubed. So on our cross section, we have a base and our height. Height is always this direction that's going, I don't know, perpendicular to which way we're bending it. But we've seen that before, so hopefully that isn't too confusing. If you are in structures, you probably know it as BD cubed over 12. Same thing, just different variable, D instead of H, but same idea. So those were the stresses we talked about. The other thing we did talk about is, we didn't really discuss it for bending or twisting or anything like that, but if I were to put an object in compression or tension, not only am I applying a stress, but that stress leads to a strain, which is like a change in length, right? Divided by the initial length. So here's our basic definition of strain, change in length over the initial length. We actually had an equation, our final minus our initial length was just change in length over our initial length. Units would be in inches per inch. And the reason we really looked at this is because then we developed this stress-strain relationship. Remember that whole thing? So with our stress-strain relationship, we said every material will have its own stress-strain relationship, where we have stress on our y-axis and strain on our x-axis. And what we really care about is this E value, right? This E value is called our modulus of elasticity, or Young's modulus. And that's a relationship between, this would have a very low E value, meaning I don't have to put very much force and I get a lot of strain. Versus if I had, I don't know, something like this wood ruler, if I were to pull on it, it doesn't, deflect nearly as much. There's not very much strain for the same amount of force. So that's why we care about this E value. It's basically how much an object is going to deform based on a given load, which is very important when it comes to materials, right? We did have these different regions we talked about. The elastic region, remember that? So this region in here, when it's linear, that's our linear region. And then we had this yielding region when it's just stretching with no additional load. Steel, at least, or metals, have this idea of strain hardening up until you get to this maximum value. And finally, we have necking, where it's getting thinner right before it breaks. So we had those elastic, yielding, strain hardening, and necking regions. Value-wise, what we're concerned with is our sigma y. It's our yield stress. How much stress can it have before it gets to the point where it's permanently deformed or no longer in that linear region, right? It's our sigma y. Usually that's what we're using in industry to figure out how strong a material is our yield stress. Sigma u is our ultimate. sometimes you could design on this basically like what is our ultimate stress before failure. Depends on what design manuals you're using. And we also have sigma S, our failure, sigma F, our failure load, right? So it summarizes it there. Sigma Y yield stress, sigma U ultimate, sigma F failure. E is that slope, modulus elasticity. So we have an equation to find this if we have two values, our stress and our strain. You can find E because it is stress over strain. We said there are brittle materials like cast iron or concrete, ductile materials like your steels. Big difference between brittle and ductile is we have that elastic, that plastic region, right? That stretchy part. Talked about energy, the area under the stress strain curve. We had two terms with that, modulus of resilience and modulus of toughness. The resilience was area under the elastic curve. So it's just that linear region making like a triangle shape typically, right? Versus modulus of toughness, we have the whole area under the entire curve. What's the difference between those? Well, resilience means that if I were to release my load, it'll go back to its original shape because I haven't exceeded this yield stress. Versus toughness is how much energy can I have before it fails, right? Before it breaks. So after that, we changed gears a little bit. We started talking about heat treatment. So with heat treatment, what you should be familiar with are the three stages. You are heating up your material, and then you have to wait. Keep it in that heat for a while, right? And what that was doing was you're in that critical range, and you're lining up all of the molecules and everything like that. Then you wait for a little bit until it's all at that point, and then you cool it quickly. And of course, that hardens your material. So what we covered was that hardening process, like I just talked about. We talked about tempering, because when we go through this heat treatment, what happens is it makes the material very brittle, right? And while it's harder, the brittleness isn't always a desirable characteristic, so we can temper it. Temper it is heating it again and then cooling it, but we don't heat it quite as much, and we let it cool more slowly. Annealing and normalizing. Take a look at the notes on these different ideas of heat treatment, right? But those were the types of heat treatment. There are more types, but those are the 4 types you should be familiar with. Some terminology within this heat treatment process: perlite, the decollescence point, austenite, recolescence point, and martensite. So what do those mean as far as the heat treatment? So go ahead and know that as well. From there we moved on. We talked about ferrous versus non-ferrous metals. So really, ferrous and non-ferrous, I had this big long table, and it'd be good to have. There's a lot of easy questions that come out of ferrous versus non-ferrous. Of course, ferrous mean that it has iron, right? So either it has iron or doesn't. Non-ferrous, we talked about 3 types: brass, bronze, and solder. How to make those, what kind of alloy are they? Brass is copper and zinc, bronze, copper and tin, solder is lead and tin. Versus the ferrous metals, then it's a matter of how much carbon is in there. We can have greater than 2.1% or less than 2.1%. If it's less than, it's steel. If it's greater than, it's cast iron. Remember, more carbon makes it more brittle, right? So with steel, we broke that into either a low alloy or high alloy. We talked about low carbon, medium carbon, high carbon steels, what percentage of carbon they have in them. For the cast iron, for the greater than 2.1%, we call those cast irons. We had the gray iron, the nodular, white, and malleable. And we had a couple other alloys we talked about in there, like stainless steel and things like that. So, but I would say this is the primary emphasis on our metal alloy section. So after metal alloys, another topic we talked about was concrete. And concrete, I went back to the PowerPoint because there was just so much information. So you can have those as your open notes part. You might want to use those. But as an overview, what you should be familiar with are the components of concrete: aggregates, water, Portland cement, admixtures. Familiar with what the general proportions are, what has the most amount of ingredients versus the least. You should be familiar with entrapped versus entrained. Entrapped is the air we don't want in our concrete. That's why we use form vibrators or internal vibrators or whatever else to get that entrapped air. Entrained is what we're adding to our concrete. It helps with our durability and workability and strength of our concrete. So we have an admixture for our entrained air. Be familiar with the hydration process. What is that? That's that, that chemical reaction between the cement and the water. It's exothermic. It puts out heat and affects the strength, durability, density of your concrete. Slump testing, you should be familiar with it. We did it, right? How do you do it? What is it? What's the point of slump testing? It measures that consistency in water to cement ratio. So more water, higher slump. Reinforced concrete. That's that idea of adding steel to the tensile areas of our concrete. So if I had like a cantilevered beam, where would the steel go? On the top of the beam or the bottom of the beam? Well, what part's in tension? You can imagine the top would be in tension because it would be trying to bend down, right? Versus if we have it's actually a negative moment, so it's causing it. Now they know more about that. If we had a normal, evenly distributed or point load, they have a positive moment, meaning the bottom's in tension, put the steel on the bottom. That's really what we're saying there. Be familiar with pre-stressing. There's two types of pre-stressing. There's post-tensioned and pre-tensioned or post-tension. Pre-stressing, all it means is we're putting tension in the steel before the beam is in service, or before the concrete's in service. And you can either do that by casting a sleeve in there and then putting tension in that tendon after you've poured your concrete. That's why it's called post-tensioning. Or I can pull it tight, pour the concrete, then release it, and either way it'll put a slight camber. That's called pre-tensioning, right? Put a camber in there. So getting into more of the design aspects, so we covered steel and concrete. Then we talked about beam design, in particular steel beam design. And to design beams, we came up with a new term. It was called a section modulus, a new variable, S. We said S was equal to the maximum moment, or whatever moment we're looking at, usually the maximum bending moment, divided by the allowable stress. So oftentimes the way these will work is the moment will either be given to you, or you'll use that same moment sheet and you have either point load or distributed load. Find out what that moment is on your beam. Allowable stress will be given to you. Usually it's like if it's an A36 steel, it's 36 KSI, something like that. But divide those two and it gives you this idea of a section modulus. Then you go into those I-beam tables, and remember what an I-beam is. It has depth by your weight per foot. So if we're looking for the lightest I-beam to support a moment, which is usually what we're doing because that's the least expensive, then what we're concerned with is looking at the second number, which is the weight, going into that table, you're always looking at that SX value, finding an SX that is at least as large as what we calculated we need. So if this needs to be 55, then we need greater than 55 for this SX. Go to that table, find the lightest I-beam. I know that process takes time, so of course if you have a problem like that, I'll make sure you have time on the exam to complete a problem like that, right? Now, we also said after we pick our I-beam, we need to make sure that it doesn't deflect too much. So it may be strong enough based on the section modulus, but it may have too much deflection. So we need to check that, right? How do we check the beam deflection? We have a table, and the table will have what type of loading it is, and you can put in your values and basically spit it out. The main thing is don't confuse the maximum deflection with the elastic curve. Remember, there's multiple columns. The maximum deflection, if I wanted to know if this had a deflection like this, maximum would be right at the center, right? But if I were to say what's the deflection 1 foot away from the edge, you'd have to use the elastic curve equation where you put in x equals 1. So you can always use the elastic curve. If you wanted to know maximum deflection and put in the length, the halfway point, you could put that into the equation and get the same thing, right? Then the last topic we talked about was column buckling. And with this idea of a column buckling, what we were saying is if I put a load directly down on a column, instead of just crushing, it'll actually start to buckle, move one side or the other side, right? It means it's not stable. Well, there's a certain load that I can push down. We call that P critical, which causes this buckling, right? We had an equation that says equal to EI times pi squared over L squared. P critical is that load that causes instability. L is our overall length of our column. E is modulus of elasticity. There's that E value again. It's, based on that stress strain diagram, the slope of the line. But usually E will just be given to you in the problem. I is moment of inertia. So remember we said I is 1/12 BH cubed, or BD cubed over 12 if you're in structures class. Well, if it's this is square, so it could either buckle out towards you or this way. It doesn't really matter. It could buckle all 4 directions with the same force. However, if it's rectangular, like this ruler, we know which way it's going to buckle. It's going to buckle away from me, right? I don't want to put too much load, it'd probably just snap, but it'll buckle this way. It's unlikely it will not buckle this other direction. So it always buckles towards that wider dimension, right? So B is always that larger dimension. For example, if I had a 2x6, which is 1.5 by 5.5 inches, which way is it going to buckle? It's going to buckle in that 5.5 inch direction. That's my base direction. So I have 1/12. The base is 5.5. The height is 1.5. So don't mix up base and height just based on which direction it's going. You have to look at the shape, right? So that's what we had. Shoot me any questions if you have any. Otherwise, give yourself a solid 2 hours in a quiet space, and good luck. I'll talk to y'all later. Thanks.